of this quantum computation course. We have something like 14 weeks to go through some aspects of quantum computation. I have split the material into 7 sections. So we will start, I will just go briefly through them. We will start today with the introduction. And the introduction will contain a little bit of the next 4 parts. The second bit will be linear algebra. Now, the linear algebra is really fundamental. So, and I didn't want to simply start with linear algebra, because then we would simply do 2 or 3 weeks of linear algebra and you wouldn't see anything quantum at all. So I thought we would start with the introduction, then go over the linear algebra in more detail. We will spend a little bit of time on quantum mechanics. Now, I don't want to worry any of you who aren't comfortable with physics. We will go through the postulates of quantum mechanics. We will accept them. I will today do some justification as to why those postulates, we believe those postulates to be true-ish. And even if they're not true, we can use them because they seem to explain our universe. And these properties allow us to imagine and realize quantum computers, and so it's quite essential that we go through it. I don't want to worry anybody though, because it really isn't necessary to have any background in physics to follow this course. Of course, it will help, but it's certainly not necessary. What will be necessary is the linear algebra and being comfortable with that. Then we will get on to quantum computation. And this is the main core of the course, I would say, quantum computation and quantum algorithms. And this will probably, around here, will be somewhere around Easter, I should imagine. Then afterwards, we will do quantum, the last 2 topics, which will be quantum error correction and quantum information. My plan is to roughly write up, I wouldn't say notes, but at least what we're supposed to have learned in each section at the end of each week. So it'll be every Thursday or Friday, Thursday afternoon, Friday morning, I will type up some kind of summary of what we've done during the week, at least the main points, so we know where we're going. The main reference book for this course will be the following. It's a book called Quantum Computation and Quantum Information. And this book is written by Nielsen Chuang. And it's published by Cambridge. And we will follow most of what we will do will be contained in this book. Okay, so obviously this is a book of roughly 600 pages. So obviously we won't be able to do everything that's in this book. And sometimes if you need more like details on what we're doing, it can be found then. So I thoroughly recommend this book. It's a very good book. Yeah, the only time we might drift a little bit will be in section 6, which is more my own invention. But apart from that, the rest of it you can probably find it there. And possibly quite a bit of 5 I took from an introduction to quantum computing. by K. La Flamme Mosca. That's the name of the book. K. La Flamme Mosca. Those three, well, all of these five are very important in the development of this subject. And this is a good book. It's a little bit more compact. So trying to start off with this book is quite difficult. Once you've read some of this, then going on to this is doable. But this is quite difficult to go straight into, I would say. But we were certainly helped a lot in chapter 5. Okay, so that's more or less the structure of the course. Then we have seven chapters, 7 topics, and we have roughly 14 weeks, so that's going to be roughly 2 weeks per topic. But I imagine these will be a little bit less and these will be a little bit more. And so that will be kind of why I think we could probably get to here by Easter or something near it. Although maybe not, because maybe it's less weeks before Easter and more after. I'm not sure. I haven't looked. Yeah, so probably important information for you. Well, you can read this anyway. It's on the file. The exams. So we will do a midterm exam and a final exam, and so you will have a partial and a final, and the evaluation will be the maximum of this with this. And my justification for this is that all of this builds on what came before. So if you can do well in the second half and you didn't do so well in the first half, you should not be punished, because it means there is a lot to assimilate, and it may be the case that by the time you get to the final, you are now more comfortable than you were in the partial exam. So that was how we're going to calculate the final marks. And the final remark, there's a couple of just before we start, there's a couple of books on quantum mechanics which I can recommend, just because I think at some point, I hope, you will, this subject will also pique any curiosity, some curiosity to delve deeper into quantum mechanics. And I think a quite useful book and accessible books are Quantum Theory by Ferris and Quantum Mechanics by Modern Quantum Mechanics. By Sakurai. But I have to stress, it's really not necessary. Nothing in that book in these books is necessary for this course. It's just if you get interested, then you may well do as the weeks go by. They're quite, I would say they're fairly accessible, and you will see at some point that we will have covered some things which appear in this book. So these books. But as I said, this is not a physics course, so don't worry if you're not comfortable with physics. Right, I think we can begin. Any questions? Okay. So as I said, the introduction is going to be a little bit of a mixture of what to follow, like almost a tapas of what's to follow. And that's following the style of, it's me. That's following the style of Nielsen and Chuang, who take the same approach. Before I start with qubits and let's say the real part of the course, I just want to spend a little time 1.1, this is going to be talking about some experiments, because I think it's a good thing to know where does quantum mechanics. Oh, there we go. Where does quantum mechanics come from? Why we got this these postulates, and why can we use them? How on earth did we come up with that in the first place? And I think you could trace it back to various different moments in time, but a good place to start would be with the following experiment. So imagine you had a barrier set up with two slits in it, and let's imagine for the moment that there's water going through these slits. So coming through here is water, and coming out the other end, this slit causes some waves here, and this one too. And if you set up, let's say you have a harbour wall here behind it, what you will see is higher splashes somewhere and then lower splashes, and sometimes these waves here coming through the slits will cancel each other out. Okay, so you kind of see this if you go down to the harbour, and you're quite used to seeing waves coming in, and sometimes they join together and make bigger waves, and sometimes they cancel each other out. And you can see that on the harbour wall where it's splashing. Now, in 1801, a guy called Thomas Hardy did the same experiment with light. And the reason he did that was he wanted to show, because he suspected that light travelled as a wave. And he did the same, shone, now the slits are much closer together, shone the light through, and indeed saw what they call an interference pattern on the wall behind, and concluded that light indeed travels as a wave. Okay, well, no surprise, until roughly around 1905, Einstein is trying to understand what's called the photoelectric effect, which is trying to knock electrons off a silver plate or something metallic plate, and by shining light on it. And if light travels as a wave, appears as a wave, this was not giving the results that they expected, and came up with the idea that light actually travels in small packets of radiation called photons. Well, Einstein himself didn't give it the name photons, but guess the light is actually made up of small particles called photons. Now, that's confusing, because we just thought it travels as a wave. So what would happen if we repeated Thomas Hardy's experiment, but now sending the light source one photon at a time? Now, when the slits are now much closer together, so when the photon comes here, it has to decide which one of the slits it's going to go through. Well, if it goes from the left and the right, so what you expect to see behind it is two bands of light, where the ones that went through the left slit and the ones that went through the right slit. But you don't. What you see on the wall is an interference pattern. the same interference pattern is when you send it through as a continuous stream of light. Now, our argument for the fact that we had this interference pattern was the fact that the waves were coming through and joining together or not, making bigger waves and cancelling each other out. But how can that be if you only send, how can we get an interference pattern if we only send through one photon at a time? One possibility is the photon actually went through both. It went through both with a probability or in some kind of what they say superposition state. Okay, so this is one of the kind of, and then interfered with itself to create the interference pattern. It's a little bit crazy, but that's one explanation. That's a possible explanation. Now, well, obviously this made physicists very unhappy. So what they started trying to do was trying to work out, okay, well, hold on. Surely, if we just like look at it here, we can set up some kind of experiment where we can look and see which slit the photon went through. And in that case, if you do that, then unfortunately, what you see is this. So if you try and work out which slit the photon went through, you will just see two bands of light and no interference. So somehow looking at it changed it. It forced the photon to make a decision. Okay, so we will come back to this when we do the postulates of quantum mechanics properly. But it's worth seeing these experiments now just to have an idea of where is all this coming from. Okay. Now that was one experiment. I'm going to use just another 5 minutes with another experiment, and then I promise that we will start the course. We will start the introduction. Okay, so one more experiment, which we will come back to. So I want to draw it. Hopefully I won't rub it out. Okay, so this is still 1.1. So time going forward, we are now in 1976. Let's find the experiment. Now, we send light. We have a light source here in the torch. And light comes out here. And, will I get this in white one now? Yeah, this one. Here, we put a beam splitter. Now, a beam splitter what it does is it lets half the light go through and reflects the other half of the light. I like to think of it, I don't know if this is correct, as those kind of half-painted mirrors you see when the police are interviewing the suspect and they can see through the mirror and not, but I don't know if that's actually true or not. Anyway, this is a half-silvered mirror, and it lets 50% of the light go through this way and 50% of the light goes that way. Okay? Now, here we've got a mirror. And here too. And then they're going to go down here. That's going to go up here. And we're going to put the receptor here. And a receptor here. And no surprises, because this beam splitter split the light 50% went this way, 50% went that way. Bounce off the mirrors, we get 50% of the light on this receptor and 50% here. Now, with Peter, first did, is he said, okay, what happens if I put another beam splitter here? Well, logic tells you that these 50% will go through and 50% go up. And for these 50% coming up here, 50% go up and 50% go across. 25% plus 25%, we should still see 50% here and 50% there, right? Right. We get 100% here. Now, the explanation for this is the same as the previous experiment, in that the photon didn't travel one way or the other. Possibly it traveled both ways. I will leave that up there because we're going to come back to that experiment. But let's start now with a kind of idea of what's going on. So let's say this experiment gets even worse in a minute. And you could also do the same thing as the other one and try and look at the photon and if you observe it again, like with the two-slit, the double-slit experiment, again the photon will suddenly decide, oh yes, I went round that way. Okay, so then you will not get this result. Okay, it's only if you don't observe it. Okay, so let's try and put some mathematics into this. By introducing the concept of a quantum bit. So let's say a two-state quantum system is represented by a qubit. So we will denote these states as 0 and 1. Okay, so that's just thinking about our two-state quantum system as having two states. Now you can, it may help at this point to if I tell you that everything small enough will have quantum properties. So rather than, you could think about the photons here, let's say the ones that are going straight through are the zero. It starts off coming out in a zero state, and going up here corresponds to the one state. Okay, but it's not just light; it's anything smaller. So you can also think about a little atom, and you've got an electron here going around the atom, and this could be in its ground state. And at some point in your chemistry classes, you learned that if you give it the right quantum of energy, this will then go up to the excited state. And then this would be, let's say, 0, and this would be your state 1. Okay, so in a way, it doesn't matter. I mean, in most quantum computers, they use quantum particles which are called a trapped ion, which is exactly what it sounds like. It's an ion which is trapped in some kind of container. Okay, so which is then exposed to energy, and it's the energy which lets you change the state. But, and this is the important but, you can also have a superposition. So, superposition means that, and I will call this psi. That it doesn't have to be, this electron doesn't have to be in the ground state or the excited state. It can be somewhere in between. The photon doesn't have to be going this way or that way. It can be going in a superposition of those states. Okay, now where do these A and B live? These A and B, this is living in the two-dimensional complex space. And the rule for it to be a valid quantum state is determined by the measurements. So if we, so we can only determine A and B by observing. So we can force the photon to make up its mind where it is by looking at it. Okay, so we can only determine A and B by observation. And we observe the zero state with probability A bar, and we observe the one state with probability B bar. These bar is the complex conjugate. So now I need more space. I'm loath to get rid of my little picture just yet. So this is the complex conjugate. So let me just put an arrow down. Complex conjugate. And since, of course, the probabilities have to sum to 1, we have that AA bar, AA conjugate plus B conjugate is equal to 1. So, for example, this state, we observe half the time in 0 and half the time in 1. Yeah, you end up doing a lot of root 2s in this. You'll end up with a lot of doing root 2s. Okay, so let's go back to this for a minute, a little picture here, and let's, so the mirror is not really doing anything part, just change the direction. Let's imagine, suppose, here's an idea. Maybe, just maybe, what the beam splitter does is multiply multiplies our qubit by some matrix. And let's suppose it is this matrix. then what happens to our zero? Well, yes. So I forgot to say. So this 0, 1. So we think of 0, 1 is a basis, is an orthonormal basis. For C2. Okay, so as mathematicians, we like to use, I don't know, E1, E2. Physicists use 0, 1. Yeah. At first you think, oh, it's a difficult crossover, but after a little while you become convinced that this really is a very useful notation, certainly as things get more complicated. So my advice is accept it and move on. So this matrix, this column is corresponding to the 0. This column is corresponding to the 1. So it's ordered in the obvious way. Yeah? So this is the 0 row. This is the 1 row. So, for example, what would then be U of 0 would be the image of the first element in the basis, which we know from the new algebra classes is the first column of the matrix. So that it can be 1 over mu2, 1 times the first element in the basis, plus I times the second element in the basis. Okay, all good. So after hitting this first beam splitter, our 0 state is now its superposed state like this, and then it hits this other one here, and the 0 goes to 0 plus I1, and the 1 goes to I0 plus one, which here we've got 1 plus a minus 1, and here we've got I plus I twice, so it's just I times 1. And when we measure, this is I times I conjugate, which is 1. So with the probability 1, we are here. Yeah? So 0 means go through the beam splitter. Yeah, boom, boom, boom. So the 0 keeps going up here, and the 1. So it's just an explanation. So this is a kind of like beginning of like how do they start coming up with determining what was going on? Okay, of course there was many more complicated experiments done, and the determination of Schrodinger's equation was a major achievement, and we will look at that when we get to the section on quantum mechanics. Again, don't panic, the non-physicists amongst you, no worries at all. But anyway, I hope I've had at least some kind of justification for introducing qubits, and also that operations happen with a linear map in quantum mechanics. Everything that changes, anything, even like an observation is a linear map, and judging by this is this. So now you see, of course, if you leave the original one as a theta, you get 2 thetas here. And since, as we will see, this is a quite an important representation of a qubit, it's simply easier to keep working with the thetas like this. Now, at this moment, I am now going to introduce some matrices which are going to become very firm friends of ours. Before I do that, I just want to recall that if you have a matrix, a 2 by 2 matrix, its transpose is simply reflection on the diagonal. Its conjugate, Hermitian conjugate, is this and then conjugated. Okay, this is called Hermitian conjugate. Okay, so that's just your transpose, and then you conjugate with the elements. And if two very important definitions for us. If m is equal to its Hermitian conjugate, then it's Hermitian. And if u is, maybe it should be the other side probably. I mean, it doesn't matter, it's the same, but I'm just, it's probably more, makes more sense in the sense of when you look at the bra and get to this one. So if the Hermitian conjugate times u is equal to 1, then u is unitary. Okay? So observation, if this is 1, then if your state u conjugate, sorry, u times phi. Now, if you look at the bra of that, so if you put your line here, this would be like, let's just write this as u, and then you have like the u conjugate, the u comes on the other side because this is now a row factor, and this is now being conjugated. When we look at the bra, then you see that this is then equals 1. So a unitary transformation will not will take a valid quantum state to another valid quantum state. Okay, so this represents the unitary. Unitarians. Okay, so the unitary, the fact that it's a unitary, it will be after you've applied u. Yeah? So when you do the go from the ket to the bra, then you have to conjugate all the Hermitian conjugate of u, and since it's unitary, this is the identity. So you just get back to what you were before. Okay.
Wait, can you hear me?
Hello? Yeah.
Yeah, wait. And there, when we multiply by the u, like,
yeah,
you forget the bar, and also like when we do the bra thing, like, isn't it conjugated automatically? Like, why do we have the Hermitian? Oh.
Yeah. So the u is onto the bra. So when we.
Oh, okay.
So if we look at the conjugate, then this comes outside the bra. I shouldn't put these lines in. Yeah. So the lines are important.
Okay. Okay. Yeah, I think. And then could we also put the u inside, or it's not written like that?
Then yes, you could. But then you have to think, if you put the u inside, then it has to go on the other side again.
Yeah, it has to go on the left and without the cross.
Exactly.
Right?
Exactly. Yeah. Exactly. So you could, in theory, write
Yeah, okay. Yeah, this is what I had in mind.
Yeah. Yeah, good. So it's a matrix. This is this. I don't know what equals, because it's not really equals, it's equals a matrix. I was going to talk about, so let me introduce some visual anyway, right? So we have to that because we want to make sure we're all on the same page. So let me now introduce four matrices which will become, this is the identity matrix. These matrices are all Hermitian and unitary. And they will become our best friends over the next 2 months, 3 months. Because it's a really, really nice set of matrices, 2 by 2 matrices. Firstly, it's a basis for the vector space of 2 by 2 matrices. Secondly, if you multiply them together, you kind of almost get a group. I mean, if you multiply x and y, you almost get a z. Okay, I'll do the one. X times y is going to be I, 0, 0 minus I. So that's I times z, etc. And I leave that because it's one of the exercises to go through all of those identities. Okay, but more or less, if you throw in some coefficients, then you can make this into what's called the Pauli group. So these are called the Pauli matrices. Paulis. And I might say Pauli sometimes because it depends who I'm talking to. So sometimes we call this Paulis. I think it's meant to be Pauli, but in Spain we say Pauli. Yeah, and sometimes the identity is not included. So this is really 1/2 of the identity plus my vector r, which is where the r comes from. So now I'm going to use it. So this would be r we had before. And this is r dot x, y, z. Okay, by this I mean the normal R3 dot product. So this times x plus this times y plus this times z is equal to that. And you can see the z, you see the identity in the z, right? That's cosine times z. And the rest is right into those victorious. Yeah, I think you can verify that with your eyes. So what we will see in exercise number 5 is how certain operations allow us to move geometrically this point, which is representing our state of the block sphere. Okay, so the sphere we saw before was called the block sphere, and this is R is point on and so what we'll do is we will see the various unitary transformations related to the x, y, and z, how they affect this qubit, this state. Okay, so this rank 1 matrix, and then looking at this representation of that matrix of the point on the sphere, you will see that it's rotations around different axes. Okay, so which will come into use for much later when we do quantum computation. Okay, so that was a little delve into single qubits. I still have quite a bit of time left, so I shall continue. I will take a short brief sip of water. Now, we've been considering only one qubit up till now, so this is going to be 1.3, and we're suddenly going to have a look at multiple qubits. And we'll start off with 2 qubits. So 2 classical qubits can be in 0 or 0, 1 or 1, 0 or 1, 1. Okay, so depending on n bits, you have 2 to the n different possible states. But a pair of qubits can be in a superposition of these states. So for a 2-qubit quantum system, this psi is a valid state now, I'm just going to write my this is a four-dimensional. This is a four-dimensional vector space. Now, I'm taking each one of these as a basis. So thinking of this considering orthonormal basis. The wrong place. Orthonormal basis of C4. But I prefer to write it, and you'll see later. I mean, you can almost see it here, right? Why am I writing it as C2 tends to 2? It really is just C4. We've got 4 orthonormal vectors, but later we'll see that it's far more comfortable for us to think of these things as a tensor product, because the first thing here will correspond to the first qubit. It has a physical meaning for us. And the second one corresponds to the second qubit. It has a physical meaning for us. So it makes much more sense for us to think of this as C2, our qubits, times tensor, the number of qubits we've got. Okay? So don't worry about that for the moment. It won't matter. What's important is that this is a valid state. It's a valid quantum state. And what would be the condition now? Before we had AA conjugate plus BB conjugate is equal to 1. Well, now it's going to be, I can measure these 2 qubits, and the measurements will give me this since if we measure both qubits, observe. Okay, so think, which way did the photon go through the slits? So you showed me. Suddenly it says, oh, I was in 0. Since if we measure, observe, we get 0, 0 with probability a bar, etc. Okay, so we observe this state with probability a bar, etc. So the probabilities with probability. I mean, some ways which are shorter. But we can do something with this. These are physically different qubits, so it's quite possible they're separate. Now we have a look at one of them and not the other. Okay, so we can observe, if we observe just the first qubit, what happens? Well, what happens is this kind of collapses into, well, let's say we observe 0. So if we observe just the first qubit and observe 0, then after the observation, the quantum state is, so it's 0. So it's fallen into one of these two. But there's something wrong with this state. Let's call it phi dash. Because now we don't know this AA bar plus BB bar and this is 1. So we have to divide by the square root of this to normalize the vector. Okay, so when we get on to doing some calculations, and some of the exercises are just purely calculations, which I think is important because it really gives you a feeling for what's going on. And certainly when you do when we get into doing measurements more formally, it's good to calculate these probabilities and then work out. And the mistake I always make when you do multiple steps is to renormalize. You've always got to remember renormalize. I can't get to the answers wrong, and it's usually that. It's usually because I forgot to renormalize. Now, this is remarkable because what would happen so if this is an example, if we have a quantum state which is simply 0, 0, 1, 1, and we observe the first qubit and get 0, we know the second qubit is then 0. Okay, so that is remarkable. So it will be I'll probably use those two pretty much interchangeably. So why is this? I mean, you can see that it's in a way ridiculous because these things could be, and this is what we're going to exploit probably on Thursday. It could be, well, definitely Thursday, we're not going to get through that today. It could be that you can physically split up the location of these two qubits. I can do something here and know what's happened over here. Now, surely that gives me some power to do stuff. All right? So that more than anything, more than superposition, is the power of quantum mechanics. That's the power that we want to use in our quantum computers. It is what is called, this is called entanglement. So this state is an entangled state. I think it's fairly obvious why. We will define that more formally later. And these measurements, the measurements are correlated. So, and it's more than anything entanglement which really gives us a huge possibility. Because if you scale up now from 2 qubits to n qubits, okay, you can store lots of information because you have 2 to the n coefficients in your vector space. Think about rows of zeros and ones in the basis. But you can only observe, if you look at it, you can only get one of those bits of information out when you look at it. Okay, so you just get one of those coefficients. Not that interesting, and in fact, no more powerful than just a normal n bits. But when you take entanglement into the picture, then you get a lot of power. Okay, so that's what we're really going to exploit. How are we doing for time? We've been going for an hour and a half. We okay to continue? Just a brief rest for a minute. I will clean the blackboard slowly. yeah, so Thursday we will get to see some use of this in action. Okay. So I wondering if I could do it now and just quickly change the order. No, because I've had to explain here. Okay, there's a reason. There's a reason it's in that order. Okay. Oh well, not to worry. I've now lost page 4. Yes, of course. I can't, so to be able to tell you what I want to do, I need to tell you first about how we write up quantum circuits. Now, those engineers amongst you are going to have a slight advantage because you will have seen all these Boolean functions and these circuits before. The mathematicians amongst you, and the other ones, don't worry. I mean, you'll kind of, it will all somehow seem familiar. So this is a very brief tap out of the what's going to come later in the chapter on quantum computation. So classical circuits consist of wires and logic gates so you have your 0 and 1 coming in, and you have a result coming out. This circuit symbol is an AND. I'm just going to give you the then I'll show you what they are afterwards. Okay, so this is how engineers write down these different circuits, and I'll give you the mathematical description afterwards. Not. I should have written that. Or not. No. So this is NAND. We've got an AND and then we knot it. And then we get the mathematician's favorite, which is XOR. And so let me just tell you the truth tables, then you'll see what they are. So you've got two, well, in most cases, you've got two inputs coming in. So here you would have your input and then if you to have and, you see, you need to have both being 1. You need x and 1, you need to have a 1. Otherwise, it's going to be 0. So that's why you call this one and. So it's just these Boolean functions and two inputs. The or, well, obviously, you just need either of them. The not is just take 0 to 1, you don't want 0. NAND does the and then knots it, so this would be 1, 1, 1, 0. And the XOR would be the sum modulo 2, which is why it's part of the mathematician's favourite. So not. Okay, so we have quantum analogues of, for example, the NOT gate. So the quantum analog before we get on to that, somebody is going to have to do exercise 1, and there's a couple of exercises on the circuits. The reason that I put those there was just so that we would know about them. And one of the interesting things, one of the interesting questions that you have in normal circuits, Boolean functions, is which of these sets, if I just take, for example, the XOR and the NAND, can I make, just with those two, every single function on n inputs? Okay, so can I make every single function from 0, 1 to the n to... Yes, let's not talk about quantum computing. I don't know if I did it in that way. Yeah, so let me say that first. So which a set of gates from which we can so you've got n inputs and n outputs, and you can want to be able to calculate absolutely any function from those inputs to there. So you've got n wires coming in, you've got n wires coming out, and you want to be able to calculate any single function that comes from there to there. There's a set calculation method is called the universal set. One of the exercises will be to prove that, for example, NAND. I forgot some plans. Okay, there's two more operations which I forgot. There's this one, which is called fan out. Okay, so there's two more gates. Yes, you can take a 0 and suddenly you've got 2 zeros. Okay, so fan out and NAND is a universal set. So that's going to be one of the exercises. The first thing you have to do, is prove that with just some of these, you can calculate all possibilities for 2 inputs. So how many functions are there? Well, you've got 2 times 2 times 2 times 2, 16 possibilities for these columns. Okay, so you can first prove that you can do these 16. I would say probably just prove that you did 16 using and, or, and not, and then prove you can do and, or not using NAND and FAND. I would say it's probably easiest to do that way. But usually people find better solutions than mine, so maybe that's not the way to do it. I've written here that XOR and fan out, this you can see, XOR and fan out is not a universal set. And that's because the input is always the same as the output modulo 2 of these two. Okay, so if I put, well, that's not true. The sum is always the same. That's also not true. I'm not sure about my proof now. The sum of the input is A, and the sum of the output is as well. Anyway, well, as an exercise, you can prove that XOR fan-out is not a worry.
If the input is 0 modulo 2, it will keep being it, or something like that?
Yeah, that's what it should be. But is that true for fan-out? I mean, if I go with 1...
Yeah, but if I have zeros on fan-out, like, if I only have zeros, I cannot have ones, never, because like I cannot get ones from zeros.
Ah, yes. Okay. Yeah, you cannot get ones from zeros.
Yeah.
Okay. So let's just now have a quick look at how we would look for a quantum analog. So a quantum NOT gate, would take zero to 1 and 1 to 0. Okay, so now in quantum mechanics, everything works linearly. So we get A we will get this map for our quantum NOT gate. And we've already seen this. This is X matrix. Okay, so remember that X was 0, 1, 1, 0. Okay, so we already saw that. Okay, so with we still use wires to represent quantum circuits, although they're not physical wires. And generally will represent, you generally represent time. Okay, so we will still write down a circuit. So in a classical circuit, you would have like n wires coming in like this, and this will be our first qubit. And down here we'll have our nth qubit. Okay, so we can have up to n. Sometimes we will have many. So it looks like it's going to sit on a wire, but they're not. I mean, they're probably sitting in some kind of enclosed environment, trapped iron or something in some kind of container. Okay, so could be dots on a. Well, I mean, it's amazing once you start looking into this, and you can get lost for hours reading articles about how to make quantum bits on silver plates with spattered with stuff. But But I'll leave you to look into that in your own time. So let's take a look at an example. So we have an example of a quantum circuit would be something like this. By definition, this thing here has the following effect on this 2 qubits. Okay, so it has this effect. So this is the input before, after. This bunny goes down here. And this is called the controlled knot, right? Or otherwise shortened to C knot. Because if it's 1 on the first qubit, then it knots the second one. Otherwise, it leaves it alone. Okay, so it's a controlled knot. So let's just write that down. It's incredibly important quantum operation, quantum circuit is. So if first qubit is 0, does nothing. If first qubit is 1, applies not to second qubit. I think I'm running out of powers. I think I might terminate pretty soon. Let's just see then what yeah, so if you wanted to write this in one line, you would say AB goes to A. I mean, we use this notation quite a lot, where this is addition modulo 2. So I'll just leave you. I think I'll leave you today with just a kind of observation, which is kind of a difficult thing to get into our heads. But at some point before we get to chapter 4, we have to try to at least assimilate it. And if not, then we will get there in chapter 4 for sure. Is that into our quantum circuit, our innocent one looking like this, just this little one here, we can feed a superposed state. So it will take A00 plus B01 plus C10 plus D11. It will go to A00 plus B01 plus D10 plus C11. Okay, so that seems so innocent, but do you see the difference is like on one quantum thing has suddenly can do a whole 2 to the n changes at the same time. Okay, which with a classical thing you can't do. So that's another thing we're going to try and exploit. We will do that again also on Thursday. So on Thursday we will have our first look at building a quantum algorithm. We will start off with something I absolutely love. Well, I've got to finish a little bit more on circuitries, but then we will be able to do our first amazing thing, which we will prove that underneath all these hypotheses that we've been looking at, we can actually teleport a quantum state from one place to another. Okay? Teleportation. And this has been verified experimentally, and I will go through all that as well. Okay? Which is just an amazing thing. Okay? So you can prepare, using entanglement, you can prepare a quantum state here in Castelldefels. I'm in Castelldefels, by the way. And you've taken your quantum bit to Barcelona. I can measure I can do something here that suddenly this quantum state, exactly the same quantum state, is now in Barcelona. Now, that should defy Einstein's theory that nothing travels faster than light. Okay? But we will see that it is consistent with nothing traveling faster than light. Because there's one little thing that I haven't told you about that you have to do. But it's still possible, okay? It is possible to transport quantum particles, and presumably, some point in the future, human beings. And we don't have to, if you want to go to Australia, you can just step into your quantum teleportation. And anyway, I quite like those long flights. I shall miss them. Let's stop there. Hopefully I'll see you all back on Thursday. Any questions, any comments? No, I hope it hasn't been too, I hope I'm going slow enough here. I mean, there's a lot to get through, but we've got plenty of time, so I don't want to go too quickly and introduce too many concepts at the same time. I'm well aware that there's a lot of different concepts to get our heads around. Okay? Bueno. Fins dijous. Hasta jueves. See you on Thursday. How do I start now?